ready. We're all ready. Let's go. All right, so I was going through my notes to see what is it that I haven't covered yet, because we are sort of getting towards the end, and I wanted to kind of pick up the pieces. And believe it or not, I realized in Chapter 1, I didn't go over all the little data structures, nor did I go over all these little nifty examples here. And the nifty examples I want to go over today are here, the basic source code examples, which is going to be oc-b code.zip if you download it. And this, by the way, is, let me show you where to find this, is in Object-Oriented Programming in Objective-C. And down with the source code examples. And then right here on the top, actually, it's like the way towards the top of the list is the examples. You're going to like these. There's about, maybe a half a dozen or a dozen or so different examples I want to go and show you. But the topic of today is catch-up from previous weeks of items. And data structures are actually the structures themselves and the concept of using data types. I know I've gone over all of the examples, but I never really covered this material. So this is what I wanted to do today as part of the objectives. So Objective-C arrays. We've seen NS array, but we also have seen the C components as well, and know that anything that's available in C is also available in Objective-C. So we have the array concept, and it's actually interesting and very similar to C arrays, but you can initialize the whole array in a list, and you can actually make the list dynamic as well. Or static, in C you're looking at static arrays. Objective-C you can actually do dynamic concepts with it. Or you can just initialize a few indices in the array, or the rest is set to 0, or do a mix and match of both. And these are just some examples here of different ways you can set them. Most of them are available in C, but some of them, like the example, actually all four of these work in C as well. So know that you have the same capabilities as you do. In fact, that's why if you're learning Objective-C and you don't know any other language, C would be a good language as a base to pick up one of those for dummies books or whatever on learning stuff like about variables and variable types and arrays. It comes in handy further down the road when you want to program with them. On the multidimensional array as well, mentioning that you can initialize them in subsets as well with brackets. No comma after the second subset here. There's no comma after the second one because it's at the end. And subset brackets are optional, and the compiler will fill in the blanks as it can with a one-dimensional array. So as this one here is filling in the blanks, you're only giving it the second dimensional. Same as C, believe it or not. It works the same way. So arrays as functions. So arrays can be passed as arguments to functions. They can in C as well. Function will print, this one down below will print every integer in an array, but it needs to also be told how long it is, the array length, same problem you have in C. So the statements here with the hard-coded indices such as array 4 are potentially dangerous because we don't know. We have the same kind of static allocation, only goes towards a certain length. If we write past that length, we're going to have a problem. So here's the example. It's a function, and if you haven't ever seen one before in C, it looks the same way, except for this NS log down here on the bottom is a little bit different. So the function call, it takes on an array as an argument along with an integer value for the length. And then it sets the value here using 4, kind of arbitrary, just putting a number in there. Meaning that it's kind of dangerous because we're assuming we have 4 characters, or 0 through 3, I should say, indices. And we know that arrays start out with 0, I hope, at this point, and they go to 3 if we have a 4-length array. Believe it or not, we can use structures in Objective-C. So that's what I was saying before. If you want to learn any other language, C is the language you want to learn, actually, because Objective-C is a subset of C. So the structure and the union, believe it or not, are both supported in Objective-C. So similar to Objective-C, the struct can be initialized in one go as well. And you can use the dot member notation, which does work. You don't have to use the Objective-C method call pattern or message or variable pattern. You can actually use the dot notation for that and get at each one just as if you were writing it in C. So the values here, use the correct order that you use some unknown value in. So use the dot member notation or just use values in the correct order. So in the following example, we explicitly define the last member, but the others are undefined. So we have this example here of the structure student, and we have 3 integers in there. And then we have a structure student my career, and then we've got, we're going to set the dot, and we're just using this notation. You can actually do this in C as well. Works the same way. So dot well spent dot, but normally you're going to make a instance of a student and set the student, my student dot something, my student dot something else. So here's poor life decisions. What is that? Poor life decisions. It looks like it's going to be set to 3, 8, and 3. And then we have student unknown. We got, well, it's not unknown, it's going to be 3. So basically showing you that you can use structures essentially in Objective-C. And then the define plus declare plus define a structure in 1. Same thing that you can do actually in C. So similar to the older C style notation. So the example here will declare coffee order structure and then immediately define an instance called complexity group. So immediately after the declaration, we're putting in here the definition. Because this is the declaration, we can just piggyback it on the end and create one. So it's a little shorthand. And setting 7 and 4, meaning it's plain and double espresso, is set to those 2 values. So the bit fields are also supported, although I'm not quite sure when you use them in Objective-C. You use them in C when you have embedded systems or you have a very low memory, very low storage space, and you want to kind of conserve memory. So work on devices with very small memory limitations. You can manually define a bit size of variables and use at the bit level. So using a structure with all 3 members are packed together efficiently. In the next example, we're going to use a 16-bit unsigned integer with a 3 on and off bit flag and a 10-bit number and a 3-bit number. So note that it's valid to use a Boolean operation on a single-bit operation as well. And here's kind of just the example of it. So we're fitting into little memory location. We don't actually have to worry about this in Objective-C or on the iOS platform or the OS X platform actually, because we have our own garbage collection going on. So if we ran out of memory, well, the system would actually just create some for us by getting rid of some stuff we didn't need. So it doesn't really matter if we overallocate to a certain point. However, you might run into a situation where you're running it on a proprietary device, a small embedded device, and you want to conserve the memory. We're just using an unsign as an example, unsign ints, and then setting the precision to 1 single, to :1, 10. So it's allowing us to set the size of the variable that we're using so that we can conserve the memory a little bit more efficiently. Also, the use of the union allows us to do that as well instead of a structure. So using a union allows ambiguity. Actually, it was allowed polymorphism originally, but because a weight, it could be represented as a float, a double, an integer, rather than 1 or all of them together. So union only takes on 1 value per each variable that's declared of it, and it can switch values and switch data types. So usually for allowing for 1 storage area to hold different variable types. So unions actually make it efficient as well for low memory space. It can only hold 1 variable at a time. Must be careful to ensure that retrieval matches the same type it was which was last stored. And that might come in handy for storing lists of data. That might be of different data types. And the next example gives you a potential practical use of it, recording to store data. Here's a structure has a character to indicate the type of data recorded in the data. So we have one of the following: a letter, an integer, character, an integer, or a float value that's being assigned here. So fitting into memory for a union, only one of those values would be used instead of all 3 of them. And then we know we have declared our own data type, and then when we make an instance of this data type, we use this as if it were a data type. So just as if it were integer or float or double, we would say one of the following last space on the phone, and then last space on the phone dot letter or dot count of would equal something. It's only 1 value at a time though. So as soon as you do this, this goes away, and now only this is being kept. They're not keeping. If you want to make it keep all of them, you just take the union and turn it into a structure. Why do they have these unions and structures to begin with is because you want to put basically multiple data types all together and house them together, but you don't want to create an object out of it. So unlike a class that you would declare that would have member functions and data members and all of the inheritance and the hierarchy to it, structures are a flat line, no hierarchy. Although they're the same, you can actually put methods, functions inside of a structure and a union actually. But they don't make sense inside of a union, and inside of a structure, if you're going to do that, make it a class, and then you can actually use object orientation with it. But the structure was the non-object oriented version of the class as it was implemented originally. So here's the recorded data with a name, and here's inside we have this union that's also defined, so they can be nested together as well. So. Alright, we covered the memory management part earlier on. As I was saying, I'm playing catch up today with some stuff that I didn't give you originally. But we talked about alloc, and we talked about using constructors, and we talked about the need not to have to deallocate. And we know that allocation exists for every object that we're going to create. And whether or not we're using automatic reference counting or not, we still allocate and we still initialize objects, and we know the syntax for it, I would hope at this point. And we know that this is a reference, so we can go hello world and then asterisk p, put a semicolon right here, and the next line underneath go p is equal to new, or excuse me, now I'm doing C++, hello world alloc, and then we can put an init in there as well, and then we know that the init's initializer and the alloc is just allocating the memory. And we know what reference counting means, I hope, but I didn't actually cover the PowerPoint on it, so I'll go ahead and just refresh your memory on it. If we're not going to use the reference counter, then we have to do our own retain and release. So because we click that little button that says use ARC, automatic reference counting, we don't have to put any more retains or releases in there. So we leave that out completely, which is kind of funny because I see people's code, they send it to me for the assignments. Is this okay? And I'm seeing automatic reference counting with a bunch of retains and releases. And I'm going, well, either you borrowed the code from somebody else, and it was an old project, or you haven't tried to compile it yet because you're going to get an error message on those lines of code. Because those lines of code don't work anymore if you have automatic reference counting selected. But the reason why we're doing automatic reference counting is because we don't want to, it's not because we don't want to do a retain or release. Is that we don't want to bother managing it ourselves, and we're going to let the runtime manager run it, and actually can do a much more efficient job than we can sometimes, especially when you need to automatically or don't allocate it or delay the allocation. It'll actually do a much slicker kind of job managing the memory for us. And the counter is one after an allocation exists. In automatic reference counting, so this is what I'll do. In fact, I can say it now because there's nobody here. This is kind of the multiple choice kind of questions. Actually, as I was going through my notes, I was trying to write the exam. I have half of it written already. And I started going through things. I'm like, oh, I never gave him this lecture, which is why I'm giving it to you. And I never showed him these examples that I'm going to show you next because I have questions from this. An example, when you alloc, the counter is set to 1, but it doesn't count. It's not a counter. It's an automatic reference counter, so the multiple choice question will say the automatic reference counter counts the number of references that exist. It doesn't. It's an on and off switch. Is it being referenced or is it not being referenced? But it doesn't work like a counter, although the word automatic reference counting, might lead you to believe that it does keep a count. So it does not count how many references exist to the object. So that is actually one of my multiple choice questions. And no, it doesn't count. So instead, it's either going to be on or off. It's a switch, and if it's on, we're going to keep it. And actually, what ends up happening is it goes to the end of a list that becomes a low priority for collection. Because eventually, what will happen is it will start to collect. If it runs out of memory completely, it has to take something out. So it looks at when was the last time it was referenced. And then if you think about it, it's a time-activated kind of thing where you can't have any say on what happens here. But it's usually the last one referenced is the first one that's going out the door, because that's going to be most likely the last one you're going to need. You're not going to be needing it because you haven't used it in such a long time. but only when the memory gets down low. It doesn't keep track of it automatically though. In fact, instead of having to keep track of time and how long something has been out there, it just has an on or off switch on it. It says you're collectible or you're not collectible. If we don't need memory, it's not going to be collected. It doesn't bother. So sending a retain message to the object increases the reference counter by 1. Sending a release message decreases the reference counter by 1. If it's 1 and you go -1, then it's 0. If it's 0, it's garbage collected. It's available for collection, I should say. It doesn't necessarily mean it's going to be collected. We never deallocate. In fact, even if you're not using reference counting and you're just doing it the manual way, you never deallocate until the object goes out of existence, and then you're going to deallocate. But there's a dealloc just the same way as there's an alloc. So here we have our reference counter, which equals our retain counter. So when the reference counter reaches 0, the object is automatically deallocated. That's kind of misleading. It's not necessarily. It's just available for deallocation. Programmer does not deallocate. So the programmer only does an alloc, a retain, and a release. So rules for memory management. The method does not allocate or retain must also, a method that does an alloc or a retain should do a release. So there has to be a balance between the two if you're going to do it manually. You can still do it manually, and the reason why you want to do it manually is what if you want to retain it in between views? You've got a view that's going to come up, and you're going to have another view that's going to come up, and you want to keep everything current. You might want to retain it. You might want to turn it off. In fact, it does come in handy with pop-up windows and views and certain things. And it's in the design of the way you're keeping something and showing something. But for the 99.9% of the time, you can just let it go and have it reallocate. Because if it's not in memory, it'll just load again fresh, which is what it's supposed to do. So if a method does an alloc and then returns a pointer to the created object, then the method must do an auto release instead of a release if we have a pointer. So the calling code can do a retain release. But it's not a must, actually. So the auto release does it for us automatically in terms of the method. So we saw that actually. In fact, I think I have an example. We have it here, actually. Remember, the auto release pool still comes in handy. You can create an auto release pool. You're not going to be doing this with automatic reference counting, however. And then for the auto release to work, the program must create the auto release pool using this kind of syntax here, where you're going to create the pool, allocate it, initialize it, call it a pool, and then you're going to drain the pool at the end. Well, you're going to release the pool, drain the pool. But when Coca is used for the auto release, it's created automatically. The programmer doesn't need to do it. It will be created automatically for you with the automatic reference counting. But to release the pool and all the objects in it, you go pull release or then pull drain. Why do you want to do that? You stick everything inside of the pool and then you get rid of the pool. Otherwise, you got this over here, that over there, this over here. And this was the automated way. Prior to automatic reference counting, it was the more automated way of doing something. But it's still valid. It's still a good way of doing something if you want to allocate it yourself. Also talked about constructors and initializers, and I gave you the lecture that was on initializers. But the constructor here, I can't remember at this point whether or not I covered it, so I'm just going to continue until the end of this, actually, which is not too many slides. So a class method that allocates and initializes an object. So if you had a question on the exam that says a constructor and an initializer are the same thing in Objective-C, true or false, what would the answer to that question be? False. You have an initializer and you also have a constructor. There's both of them actually existing concept. The initializer and the constructor are two separate kind of concepts. Programming neither does an alloc nor an init, but you can create a constructor to do the alloc and the init. So, okay, so they call them initializers. So in other languages like C++, the constructor is the initializer in Objective-C. So you create an initializer. We have the default initializer is just init. We have the initializer that takes on a bunch of parameters. Those are other initializers. But then we also have a constructor. the constructor existed back when we used to do we did not have automatic reference counting, and we still have it, where we can alloc and init. So we create a constructor to do the alloc and the init. So the constructor concept works on top of everything, and it's a man-made programmer-made construct. Doesn't trigger like an initializer does. So when we create a new instance of an object, what triggers automatically? Trick question. Nothing does. In Objective-C, nothing triggers automatically. If it did, why would we have to go person alloc init? We have to manually call our initializer. And in our initializer, we call this super init. If you remember initializers, nothing runs manually. Excuse me, nothing runs automatically. We have to do it manually. So the concept of the constructor doesn't exist anyway. I mean, it does, but it doesn't. It's kind of odd. So we make a constructor method. We call the method. It does all of our allocation and all of our it just constructs a new object for us. So here's an example. So I'm glad I'm going over this today, actually. Otherwise, you're going to look at these questions on the exam and go, what? What's she talking about? It's not meant to be tricky. It's just interesting. They all sound like, yeah, true. It's the same thing, but no, it's really two separate things. So the class method that allocates and initializes an object programmer is neither doing an alloc or an init here. So here's student with name. And now we have a name, and we have a GPA, and we're doing self-alloc. And then we're running init from this construct. This is an example of a constructor, by the way. So essentially the method sends alloc to self. If we're going to do a constructor, we're going to send alloc to self, which is the student class object. Instead of saying, you know, if I had a student object and I said student alloc init and have that equal to my student, that's not using the inside of, if you're using the inside of the object to construct it itself without having to do it out in main, which is why you're using a constructor in this example, is because you're going to try and automate it inside of the object, have the object self-contained, create its own memory and do everything by itself, and then out of main you just run the constructor, which is kind of different than running a constructor in C++, but anyway. Sends alloc to self. Essentially, the method auto-releases the instance because it returns a pointer to the created instance. And then not essential as the example uses an existing initializer. It does. It uses this initializer here in its student. It could do something else or initialize the data directly without using an initializer. So you don't necessarily have to put an initializer inside of a constructor. So calling the constructor, you actually have to call it. And so you say student with name. So instead of saying student, let's say this was a student object. Hopefully we got this part. We know what an ID is, I hope. It's a generic reference type. It can be assigned to any type of object. We're going to call the object stud, and it's going to be student. Without any of this stuff here, we would go alloc right here, another closing bracket, init. That's our standard way that we have initialized and we have allocated an object. So here we're using a constructor instead, and we're saying student with name, Johnny, and this. So we just initialize it using the constructor. We actually call the constructor. So the message is sent to the student class object, returns a pointer to it, and the pointer is assigned to student. And then calling the code does neither allocing nor init. It's done inside of the constructor. This is the constructor that we just did here that self-allocs and self-initializes. They used to call them convenience. If you can remember convenient constructors. Initializers are a must. They're a required part of you have to initialize. You have to initialize all the way back to object. If you don't, even the object will be initialized by super. So initializers are a must. Constructors are for convenience. Well, that's what they say. All the books say they call them convenience constructors. And I'm like, I've never heard of convenience constructors before. It's just too convenient. So convenient constructors, make it convenient to do this without having to remember to alloc and init. Why? Because you don't want to alloc and init? I don't know. Well, you can init with something. Because you know you can create your own initializers to take on 2 parameters. Here are the name and the GPA. You could write an initializer to do that. What's the difference between a constructor and an initializer in terms of its syntax? Is it option A, they're the same? Is it option B, initializers have the subpart init in its name? Or C, actually I just gave the answer. Initially, if it says, see this is student with name, which is odd because this syntax is not required, but this is just like init with name. If we put init in there, it's called an initializer. So the initializers will be named with init inside of its name. Then we know it's an initializer. It automatically becomes an initializer. And then initializer can run with other initializers. Can call previous. And then they work just like constructors. So it's customary for the convenience constructors to put the name of the class in here, student. So then you know, oh, that's the constructor. But you call the constructor. Constructors don't get called automatically. There's no such thing as a default constructor. Like there's a default initializer, but not a default constructor. Say you could program in either iPhone or iPad. Yeah. I think I don't have to cover the rest of this. Now, I didn't cover the frameworks, but we've seen this in so many examples at this point. It's kind of like working backwards. But we have the UI kit. Actually, we always include UI kit at the beginning of most. In fact, even in the iOS, for developing standard iOS GUIs, buttons, UI text field, UI this, UI that, UI views. And then we have, we know about the IB actions and the IB outlets. I think I went over this part actually in the beginning of the course, so we'll keep that out. So that was the last part of lecture 1 that I wanted to make sure I gave you. The other part was lecture 4 I had never gone over with you, but I was going to start it and then we ended the class early one day. So let me just see if there's anything in here that is worthwhile in terms of something we haven't covered yet. Did talk about runtime binding. That's where the ID comes into place. Everything is late bound or runtime bound in the Objective-C language. Doesn't matter if it's on an iOS platform or on a Mac platform. It's all late delayed binding, or called late. Why is it late? Because not until runtime that any memory actually gets allocated. So the derivation and the runtime bindings are the most essential part of the object-oriented programming. That gives us inheritance. So the syntax, the derivation is the syntactic mechanism, for inheritance. And inheritance is a semantic of derivation, or deriving one class from another class. Gives you the is-a relationship that we've seen, an object of instance or object of type this. So expresses the meaning. And so it's a mechanism by which a class acquires the methods and instance variables of another class. So that's kind of the textbook definition of inheritance. And we've seen this so many times that I don't even know if I need to go over this, but here's the example of the inheritance in Objective-C under and looking at the initializers. And so inheritance is expressed in the new class's interface declaration. Additional instance methods here, and then we have init grad student, and what are we doing here? Interface grad student colon student. So we know how to do that. Because one of the things I'm doing on the exam is actually giving you syntax and saying, well, which class is being inherited by which class? And we know here that grad student is inherited from student because of the way that the syntax is written here. All classes by default are inherited by what? NS object. Yeah. But you know, you're good though, you're close. NS, everybody comes from NS object. Do you have to put NS object in? Yes. If you don't put NS object in, which is kind of funny because Java you don't have to do that. You just leave it out. Actually C++ you could leave it out too. You don't have to put in object. But C++ is object, Java is object, Objective-C is NS object. From next step, everything is NS. So just, when in doubt, pick the option that says NS next to it. Because It's all NS. Runtime binding, I'm not going to trip you up like that either. That was just a random question I thought I'd ask. So, runtime binding is the decision that running a method to execute when a message is sent to an object, and the executed message depends on the type of object that it is. In other languages like C++, we have virtual. If you're familiar with that language, if you're not, don't worry about it. That virtual creates the delayed binding that Objective-C has naturally. In Objective-C, as long as we have the ISO relationship, we have everything available. And the method that's appropriate for the particular object that's being referenced by its type will automatically be dynamically created for you. So you can have many different versions of the same method. If you have an object that's a grad student, you can still treat them like a student and run a student method on them at runtime, which is what that means. So the message can be sent through a typeless pointer ID as well. And I have some examples actually I'm going to show you for the ID. So that was the other piece that I didn't show you. So what I'm going to do now is look at that source code listing that I gave you a few minutes ago. Let's see. Well, I guess I don't need the Wi-Fi for this. We lost the Wi-Fi. I showed you at the beginning. If you download these examples, and if you're still having problems working with, as an example, any of the assignments, what I'm going to do is kind of go through each one of these and real quickly actually and just show you, because it's better than talking about the concepts. I just talked about constructors. I'm going to stick constructors down here so I know which ones I've touched. This particular example, if you open it up, and they're all, they're not iOS, they're all general OS X applications. My nose is bugging me today. I may have done this one with you. And in fact, part of this, what I'm also doing is pointing out where you can find additional help if you're trying to finish up some of those assignments or prepare. One of the things that I would do, actually, if I were you, is just go through. Let me just see if I can get connected here. I think I can. I think I just have to disconnect and then connect. Oh, there we go. Yeah, you just have to disconnect and connect again. You could go through. This is where they're at, actually. Right here is basic source code examples. You can go through these, and if you understand what's going on in each one of them, you should be okay. Because most of the questions actually come out of these examples in terms of the syntax and stuff. So the constructor example here out in main, it makes an instance of an object. And let me take this stuff away, make my view a little bit better. And we have an object fraction in here. And this is using the auto release pool. Some of the examples are actually using auto release pool because they're kind of old. I could have taken it out, but I didn't do it that way and just left it in there because it's okay. You can still do it. And we're creating here using an initializer, the default initializer, and then initialize with number 3, numerator 3, denominator 10. So we're making 3 instances of fraction. Inside of fraction, we have an initializer here, and in it with numerator and denominator. And then we have a bunch of methods that go along with it. This is not using property and synthesize. Instead of it's using manual setters and getters. And in the implementation, you can see that the initializer is running super in it. So the design of the initializer is basically take and run super in it. The method, the example is actually called constructors because initializers are being used like constructors in this particular case because they're constructing the objects. So if self, so this is actually pretty standard code. So if I showed you this on an exam and said, well, what is this initializer doing? I gave you some choices. It's initializing the super object, and then it's also accepting a numerator and a denominator and initializing the 2 data members of fraction with the numerator and the denominator, essentially what's going on here. And then it's returning self. If this doesn't return itself, if we can't get self, then we're not going to continue with the initializer. We're going to get an error that comes back and says can't allocate the object because you can't allocate self. Well, what happened with that is if we ran out of memory or something like that, that would cause a problem. And then we're setting values using the setters and the getters, and these are method calls. So you want to know the syntax of a general method call. You know, the this is the name of the method, colon, and then the value we're sending it. So setting in here, combining them together, set numerator and denominator, using the names for the different parameters, and then printing some stuff out. And it's an old C, but printing out fact print. This is running the method print on fact, and fact has a method called print, and print right up here is just printing out the numerator and the denominator. So, but the example is actually kind of interesting because it's showing you how to use the initializers. And it's just an example to reinforce the initializer stuff. I may have shown you that actually a long time ago. I wasn't quite sure. I know I haven't shown you this one, which would have made sense a few weeks back when we were looking at the interface and the implementation. It actually goes along with assignment number 1 that asks you to create a private method. And then some people actually told me, hey, you can't do that in Objective-C. And you're right, you can't make a truly private method in Objective-C. Methods are always public. But you can. There's a trick way of doing it. This is the actual trick, and this example is called private. So if you open that directory up, you'll see it. So in the main program of private here, we're taking my class, we're making a new instance object, and it's my class alloc with an init, and then this compiles. If I say run this public method, this one here is going to throw a compiling error because this method down here is called private method that we're running. Let's take a look at private method. Public method is in the interface. If we stick it in the interface that goes along with the .m, the .h that goes along with the .m, it's public. So that one's going to be our public method, and then it has a minus here, and it's just like a regular method. If I look at the .m file for a second, I'm putting in here in the implementation, I have public method, which is the implementation of the previous .h, but then embedded inside, and remember we saw a couple examples a couple of times where I said this is creating a private method. If you put the interface inside of the implementation file, it's private. If it's in the .m, even though you have an opening and closing at interface declaration, you've made it private because you have and this is an explicit cast to private, but you've made it private because it's hidden from the public interface. The public interface is over here. That's the public interface. It's in the .h file. So when you compile into the object code gets linked. It's only the .h files that are visible. If it's not in the .h file, not runnable. So you stuck it in the .m file instead of the .h, but it's still an interface, so you did add interface. You explicitly cast it to private. It's kind of like putting void in there. When something is void, you can put void in there. Actually, public works in there too, but there's no need to ever put public in. It's always public by default. And then in the implementation, we're going to run this private implementation of my class private. We've said we have an interface here, my class private, and then this is the syntax is different than this implementation of my class, which is going to be right here. So we're going to implement this interface, and it's just doing the same thing. It's not doing anything special, but it's still a method, so it's got a minus next to it. It can be used in here, however. So in the modern day, you don't actually have to go through this hassle here. You just put it up here in a regular interface, make it look like you could take this out actually completely. And it looks just like the other interface. You just have two interfaces. One interface is inside of the .m, the other interface is inside of the .h. That also works, not to confuse you, but this is the old style way of doing it. So when people looked at this, they go, what is that? Well, that's a private method. So you don't necessarily need this right here. And if you take it off here, you're going to take it off here too. But I think, well, we'll see. Duplicate, it's because it's a duplicate, yeah, because I've got the interface here. So we made it so it's unique. So I'll take out the, undo the typing. I have to change the name of it then, in this particular case, because I already have at implementation my class up here, so I'm going to have a problem here. So. But long story short, you're hiding it from the interface. You're hiding it from the .h, and if you hide it from the .h, then it runs actually, and it's if we try to use it, however, in fact, I don't think it's. Let's see, build successful. Let me make sure it runs actually. So public methods up here being printed out. If I try to use it out here in main from the object instance, I'm gonna have a problem with it. Oh, it's not even gonna let me do it. It's gonna say the interface is declared a selector private method. So it's not gonna work at all. But why we want to do that? Because we've done it actually in some of the examples already. It's because we want to use it inside of this implementation. We just don't want anybody in main to use it. So private's okay as long as we're using it inside of our implementation, and that's what it's there for. So we don't have to worry about it. So anyway, it is possible to create a private method. We had a couple of them with category and protocols. We've seen the protocols over and over, but I'm not quite sure if I ever showed you the category. We did one tutorial that was on categories with iOS, I believe, or something, but I just want to show this one to you to refresh your memory on the category concept and what the difference is. They're very similar, actually. So let's see, this is the category example, and here we're going to use, we're going to have, this is mule, I have to refresh my memory here. We have a fraction, same fraction as before, and then we also have, we have the print in here, fraction, math, fraction. Oh, this is a totally different example than, so this one is adding, multiplying, dividing, and subtracting, fraction math, which is going to be the implementation of a fraction type. So we're using fraction as the type in here, as the data type. And the fraction is defined in this set of classes here. And let's see, at implementation, let's take a look at the .h file. The interface is using, let's take a look here. What are we doing in here? I believe what we've done, let me just take a look here, let me refresh my memory on this one, unless this one is print, so we have the print in here, numerator, denominator, that's just like a regular old fraction class, that looks pretty normal. And we have a fraction NS object interface. It is using the category for math. No? Well, let me take a look here at the fraction. It's using the type. It's using the type for fraction inside of fraction math. Extending the library for math as a category, and the category is giving us the add. We're implementing overridden methods for add, multiply, divide, and subtract through this, and we're using the category in the terms of the implementation, which is not coming from. It's coming from the standard libraries, which is the reason why we're not including it. So, I think there's a really good reason why I didn't show you this example originally, and because it's a little convoluted, but it's just basically demonstrating the use of the category. The category is giving us extending a class without using it as inheritance, kind of like protocols. So it just adds behavior from a class implementation. So I think then the category example we did in this class, we created, and this was like in the first couple of weeks, I believe. We created a print category. We used the category inside of the classes to print the information. We overloaded it. We created a print inside of each one of them, overloaded it to print out a fraction, print out a complex number. And then we switched to protocols after that. And the protocols basically was like a built-in interface without any implementation. But the category can have some implementation to it. It can be used in a very similar way. Provides, again, standard set of methods and functionality. Here, the add, multiply, divide, subtract It's going to essentially give us the information that we're going to need for building the concept of returning, as an example, for multiplying this one times the numerator, whatever. You did the math for a fraction to multiply one fraction to another fraction. So it's going to be specific to the fraction versus a number. So, and we're doing nothing too scientific with this actually. It's just taking on a fraction. So one fraction is taking on another fraction to add, subtract. So when we run it, the divide, I didn't actually. The divide looks like it's doing the same thing as the multiplication. It probably is. Actually, they all look. Well, let's see. Wait a minute. The add is well. I don't believe that this example is a bit convoluted. I don't believe we're actually implementing the same functionality is written in all the methods. All the methods are the same. So it's not. I don't. Well, are they the same? No, it's not. This one's doing an addition here. Yeah. Subtraction is doing the subtraction. No, we're doing. Let's see. Actually, let's see if it's. Let's see if we're actually doing anything with it. Print this one times fraction, print. What is the print doing? Print. It's just printing it out. We're not doing anything with this actually. Oh, we're multiplying one fraction with another fraction. Let's see if it actually works actually. That's a good question. 1 over 3 plus 2, or no, times 2 over 5. 1 over 3 times 2 over 5. So, yep, looks pretty good. So, all right. I knew there was a reason why I didn't show you this example, but if you're looking for a better category example, we went over one in class that actually did the print method actually. So, the ID was another one I think I had gone over with you. It was people and students and employees, if I remember this right. So let's just take a look here. How convoluted? Oh, it's a fraction again. Ah, yes, this one I did with you. This one we took and created a complex number from a fraction, if I remember this right. And this one is using complex. Let me take a look at the .m here. It's coming from NS object. No, it's not. We're just taking two. Let's see. We have a print. We have a print method in both of them, and I believe we're treating them as an ID, and we're using the print method that's in both of them as their object reference. Let's just take a look here. Create a new instance, fraction, create a new complex number, then we have ID number, and the numbers equal fraction, number equals a complex, and we're basically taking and using a generic point. We're using ID as a generic reference. We don't know if the number is going to be equal to a fraction or if the number is going to be equal to a complex number, but we have the print method in both of them. So we can go number print and it's going to work because we have out here we have a print method that's going to print on numerator and denominator for a fraction. And then over here we have a print method that's going to print out a numerator and a denominator for it's going to print out a real and an imaginary number for a fraction. And depending upon how we print, if I run it, they should both print out to their corresponding print methods that's inside of the object. Even though we're referencing it from an ID, it's actually using the object instance that was created inside of the object. So the fraction is printing it out as 1 over 10, and the complex number is being printed out correctly for how it's designed to be printed out for its method. So it's demonstrating the use of the ID as a generic reference pointer, and although we have two different objects, they both have the same method, so they're both working in this context. And this was pre-protocol. If we wanted to put a protocol in here, then we'd have guarantee that each one of the objects actually had the print method. If we put the print method inside of the protocol, then we can basically guarantee that we're not going to have any problem using it generically, which is what we're doing with view controllers and things. We put a special tab view controller protocol, then we know it has something for the number of rows, and it has something for the navigation and for the cells and stuff, which is what we did last time actually. So, okay, so that's just demonstrating then the the use of the ID. You made it. I'm glad you could join us.
Yeah.
All right. Let's see. Variables and properties. This one is a no-brainer. This probably could skip this one. It's 2 implementations. In fact, I think I did this one with you as well, just to review the concept with you. Oh, is this different? And it's using, okay, so this one's using both variables and property and synthesized together. So we have a cat object that's coming from NS object, and the cat has an age and a name. And then we also have integer age and NS string name down here as properties. And then we have a print name. And then in the .m implementation, we're synthesizing the age and the name. And then we're going to print out name and age. The old days, people did this. In fact, I see this in a lot of older examples. You don't need this anymore. You can actually pull this part out of it. You don't need it. It's one or the other. So when property and synthesize came around, people left this and then they just started doing the property and synthesize. Now this has gone away. So we don't have to declare it as variables anymore. We can use it this way the same way, which is kind of interesting. So this is just a double whammy of them both together, actually. There was one I gave you already that had a car, the different types of car and inheritance, and one of the versions of the car had properties on them, and the other one didn't use the properties and synthesize at all. It just used the variables. So type. This is going to give you the what type of object is this, if I remember this right. It's going to is a relationship, or the object is of type. So let's see. In the main program, we are, what are we doing in this main program? We are creating a rectangle rec, a square square. We're demonstrating the is member of class. You needed this actually in one of the assignments that you did. And square is member of class, square class, rectangle class, and it's object class, square class. So it's just basically doing a bunch of comparisons. Creates 2 objects and does like a bunch of comparisons to see what is it a member of, and then responds to selector. Does it respond to selector size, set size, non-existent, alloc, which are some of the methods that it responds to. So we can check to see if it responds to a selector before we run the selector on it to prevent problems in the runtime. So if we know it's a member of this class, does it respond to this selector, then we can do all of the tests to make sure that it's actually going to perform what it needs to perform. So it's a good way of troubleshooting on the fly, checking to see if something got allocated or something is actually a member of a particular class. And so we have square. Square is coming from rectangle, and we have an initializer here. Rectangle is the base class. Base class is coming from NS object, and it has a height and a width. This is not using property and synthesize. So. And then on the square implementation, it's implementing a set size, set width, set height, a bunch of methods. So out in here in main, we're testing to see, do we have the set size? Do we have the alloc? Do we have, can we run that method? Which is the respond to selector, square. So square should come back true because it has a set size. But does it have a non-existent? No, I don't think it does. Does it have an alloc? Yes, it does. It can alloc. But a rectangle doesn't have a set size. The rectangle in here has a set width and a set height. Height and width. It doesn't have a set size. So if you run it, it's actually kind of interesting. You can see from the selectors whether or not the selector exists. And the selector is the method, by the way. So square is a member of the square class. Square is a kind of square class. Square is a kind of rectangle class, actually, as well. It's an object class, and it responds to set size. Square does respond to the set size method, actually, because it's a rectangle. And square class responds to the alloc method, of course, and then it responds to the set size. So interesting. It's basically just looking at the different types of objects, and every square is a rectangle, so the objects come out correctly. Alright, so that was the type. Access. What is this one? Well, let's take a look here. Public, private, and protected. Access modifiers. So if I asked you in Objective-C, how many do we have? A public, private, and protected, or the access? I don't know what I'm going to ask. I didn't ask you a question about this, but now because it kind of gives me some ideas, though. We can do an at protected, an at private, and an at public, which is going to set the access modifiers. The same thing we get in C or C++, C++ actually. So in the .m file, we don't have anything. It's just an implementation. We didn't implement anything. But in the .h, we're just setting the interface to, we have one public one, and then we have a private variable 2, and a protected variable. So if we got out here in main and we take a look, we can create an instance of A, access, call it A, and then A.public variable equals a 5, it's public, that'll work. But this one's not going to compile because it's private, and then the protected one's not going to compile either. So it's basically showing you that it's private, even though you've specified it at private. But we know we can do at private with making it in the interface as well. If we stick it in the interface, inside of the .m, it's private by default. Otherwise, this makes it private by using the access modifiers at public, at private, at protected. Which is kind of a makeshift C++ style way of doing it. Putting it in an interface that's inside of the implementation is more of an Objective-C style of doing it. So that one was worth looking at, actually. Refresh my memory on that one. Let's look at, well, let's see. This one, class, maybe showing us inheritance. Let's see what's going on. Probably not showing us class. Oh yes, class variable. This is good too. It's an example of using everything we've used so far is method to method to method to method for instances. These are class methods and classes that are not. These are class methods and not instance methods because we have the plus symbol. That I know I'm going to ask you. The difference in between the minus and the plus symbol that precedes the method. The method declaration tells it whether or not it's a class level or an instance level. So the minus is the instance, the plus is the class. And here we have a class called class, class A. Class A is from NS object, and it has two methods in here. One that's void, one that's an integer, and one is going to return the count, the other one's going to initialize. And then in the implementation, the initializer here, init, we've got init over here, and we also have initialize. Technically, initialize could be an initializer because it does have the word init in it, but it doesn't take on any parameters, so it's not the default initializer. That one's the default initializer. So we have self equals super init, same thing you see before, count plus plus. So we're going to count plus plus because we're incrementing the counts that's inside of the class. We're not going to use it outside. Instead, we're going to initialize. We're going to return the counts. Well, probably should have said return count. Initialize count is equal to 0. So in our implementation, we're just providing those method bodies. Inside of main, we've got class C1, class C2, but we're not going to do anything with these objects, which is why we've got this stuff here probably going on. Unused variable C1, unused variable C2, unused variable C3. But the initializer is we're initializing it, we're just not using it. The initializer is going to essentially increment it because it's doing a count plus plus. And then print the count here, print out the class A count is equal to something, and then here we have a class A count. We're just going to print the class count out a couple of times after the objects have been created because the initializer is incrementing it. If we wanted to, we could just run the method from the class by specifying the class name and then the method, and that would run it as well. So now we have the count going from 2 to 3. And, get rid of those warnings there. So we can see that the class the class method is running to initialize it. And the class method here, this particular case, is the init when we make the is the init count that is being that's returning the counts from the incrementing that's happening when we create the objects. And we're running init counts here. So class init count. So we're calling the init count method that could have done the initialization, and it could have probably done the increment for us as well, but instead we have to make objects to have that run automatically. So we could initialize it by making it 0. We could run that method on there to initialize it out. I don't know if we're doing that. No, not doing that in here, but I'm just running init. When we run init, that's going to increment it. So all we have to do is make instances of these objects, even though we're not going to use them, and it increments that class variable for us. And we just print out the class variable. We can do this on class A without making an instance, because over here, this one's a init count. It's going to be a plus. So these are the two that we're looking at. So, and then we can mix and match because this one's a minus. This is a method that's being run on the instances. So it's a nice demonstration of the class versus the instance variables, methods that can be used. Well, let's see. Arrays. We saw arrays in NS array, NS mutable array. We also see NS dictionary. These were the long lost examples I didn't give you before. I shouldn't say long lost. They weren't that lost. They were in there. So let's see what we have here. We've got a main program that's not doing nothing. We have no objects in here, just a main program. It's not doing nothing. It's got NS enumerator. So we're using an enumerator. So it's just like enum, where we've got an array of object enumerator. So it's a generic array of objects. And we're going to have this generic ID called obj object. While the object is equal to enumerator next object, next object, next object, next object. Think of this more of a built-in data structure. The enumerator goes through and enumerates through objects. We have a basic object list that's of an array type. So because we're taking, this print method is taking an array, and the array is going to be as an argument. And the array as the argument, we're going to take and create an enumerator that's including all of the array object elements that are inside of it, go through each one of them, get the next one, get the next one, get the next one, and print it out to the screen. And then out here in main, because this is just another makeshift kind of function, and we stuck out here to run from main. We have to put it before main, otherwise we have to put a function prototype up there. Same thing you get in C. So out here in main, we're going to create a new instances of an NS array called it array, and NS array allocate it, initialize it with objects, and we're going to initialize it with some strings. So we're going to initialize it with me, myself, and I as 3 strings. And then we're going to create a mutable array. And the mutable array, we're going to call it mutable. That's going to be a NS mutable array alloc in it. Mutable means it can change. NS array means it's fixed by how big we make it. If we fix it, then we have nil at the end of it that makes it sure that that's the end of the array. So we can find the end of the array. We can take a regular NS array, put it into a mutable array, take the mutable array, put it into an NS array, and we can switch them. They're both compatible data types. Just one of them can grow and the other one can't. Enumerate over the items. Here we're just going to run the print with the name of the array that we're sending it. And that's that method we looked at, the function that we looked at to begin with. And then let's see, add some stuff to it. So mutable add object 2, 1, 2. Mutable add another object from array. So we're going to add me, myself, and I as an object from, it's going to be an object inside of the object. As I mentioned before, it's compatible as a data type. Works. So we can add the object from the array, and then we can add the object 3 after that. And then when the print enumeration out, we're just going to send it. So we have the mutable array. So we have 2 of them. We have this array that's up here, and then we have this mutable array that's defined here, because we add stuff to the mutable array, which means it can grow, essentially. And then we print mutable, we send it back up here to print out the items, printing out the array. And then we're going to sort, then print them again. So we're going to say mutable sort using selector. What's the selector going to be? Case sensitive compare. So it's going to put them in case sensitive, compare, which is going to be alphabetical order, and then print the mutable array. So if I print this out, if I run the program, it's going to print out the array elements for me. And if it prints out the array elements for me, I've got the static array. I guess I have the headings being printed out up here. Yes, mutable array, static array, sorted array. Me, myself, and I, that's the first array we created. And then the 1, 2, me, myself, and I, 3, because we added the array to the mutable array. And then we sorted it, so it's I, me, myself, 1, 3, 2. Because we have a alphabetical order of the mutable array. So basically demonstrating how many different array options. Actually, we have dictionaries coming up next, but one use of the array. So this one here takes up more memory than this one here, because we used to people ask, why come no one just use mutable arrays all the time? Well, then in your program logic, it takes up more memory, but then it also is growable. What if you don't want it to grow? You can't do error checking to see if it's going to catch, hey, ran out of items. We already got 10 items. And it says, okay, pick 10 tiles. You're playing a game. And the game logic can only allow each person to pick 10 tiles. And then you can tell, well, it already has 10 tiles. So it's not going to grow to 11 tiles or 12 tiles. You're just not going to be mutable. So it'll trigger an error. You can do some exception handling on it or something to figure out, to basically make your logic work that way. Or you can decide, you know what, I'm not going to use arrays like that. I'm just going to use MS mutable array for everything. Because we have that in Objective-C, where we don't have that in C++. Instead, we have the dynamic array kind of concept that we can implement with linked lists and stuff like that. But we don't necessarily have a built-in mutable array for us. And we don't have an object as an array either, so which gives Objective-C sort of an advantage. Questions on arrays? Nope. Okay, moving right along. Getting through all these examples. Let's look at dictionaries, because dictionaries are so similar to arrays. We saw one the other day, actually, NS Dictionary. We saw one with the properties. We created a dictionary to hold the property items. So let's take a closer look at that concept. Make some better real estate here. All right. So again, we just have a main program. There's nothing being represented here. So let's see, what do we have here? Another print method. Who knew? Now it's taking on an NS Dictionary. And we're calling the NS Dictionary the type of variable, calling it a map. And again, we're doing an NS enumerator that works on an array, a mutable array, a map, an NS Dictionary. Works on all of these items, actually. It's a generic enumerator object that works the same way. And now we have an ID key. So while the key equals enumerator next object, well, it doesn't come back null, because while we have an object. Print it out. So we're going to print out the key description as a C string, cast it to a C string. And then the map, we're going to print out the object for key in our dictionary, because we have key value pairs. All we need to keep track of are the keys and the values that we've given for it, or the object for the key in this particular case. Using, again, print out the description of the object, and then you cast it to a C string type as well. So that's what our dictionary printing is going to look like. In our main program, we're going to do the same thing as before. 1, 2, 3. It's being added in. So we have this NS Dictionary, highly sophisticated dictionary of objects, where it says 1, 2, and 3 is equal to 1, 2, and 3. So the NS number with init 1, number with init 2, number with init 3. So are you going to use this data type here to say it's a number, NS number with init. So, and we're sending it, this here is going to come through as a number. It's NS number variable type. That's going to be in this pair here. So if we wanted to, we could just go and put like a non-number value in there, like like another string, like test or something. Get rid of this here. Then we would have a key value set that had 2 strings. So we can put a value in for any one of our keys, and we can mix and match, actually, because they're just generic object types we're putting in here. And so then we can down here on the bottom, it says Mutable Dictionary, mutable, same thing we did with the array. This one, so this is the regular old NS dictionary. This is the Mutable Dictionary, which means it can change. So we have a Mutable Alloc, so NS Mutable Dictionary Alloc, and initialize it. So we created it. Now we're going to take and print out, this is the static dictionary, same thing as before for the array. And print the dictionary, so we're going to send the dictionary up here. And then we're going to add a couple items to it, to Tom and Bob. And we're going to put in email addresses here. So my one is going to be test. Here, I'm going to hit test for one. There we go, so I know it's one. So now we got Tom and Bob, and their email addresses are going to come in here. And then now we're going to print out the mutable array by using the same method to print it out. So if we print it out, we get an interesting, not interesting, I guess, but we get the keys and the value sets that get printed out from the C string is depreciated, yes. Okay, so 3 is 3, test for 1 is 1, 2 is 2, so we're looking at the key value combinations. And then the mutable arrays here for the email address for Bob and the email address for Tom. It's printed down. So it's kind of shows you that this is a little bit more flexible than C or C++ actually. So C++ doesn't have a dictionary built in either. You have to make it yourself. You can easily do it with pointers, however, and nodes, kind of a dynamic linked list kind of fashion. So, but it's a built-in NS object here. NS dictionary and NS arrays, and then the mutable variations of them as well. There's the dictionary. So last but not least of my set of examples that I should have shown you like months ago. It's okay, we're catching up. Exception handling. So this is another kind of interesting one. Cup overflow exception. So let's see. Let's take a look at main. Well, let's take a look at the cup overflow exception. We have cup warning exception, then in cup overflow exception. So the cup warning exception here is from NS exception. So we're going to take and we're going to create our own two exceptions. The cup is overflowing and the cup is going to about to overflow. It's a warning. Now we've overflowed it because we're extending now from NS exception. So NS exception on our cup warning has got an implementation. It's not going to do anything. It's just a creation of this so that we can throw it, and then we'll get it. So we can test to see if it was thrown. So same thing here. We got cup overflow from NS exception with the implementation. There's nothing in the implementation. It's just two generic exceptions that we've created that are extended from the exception object. So they're going to get all the basic exception behavior that's associated with inheritance. So we have an object called NS exception, just like NS object, but it's a different level of hierarchy. So we've made two, and then we have cup up here. So cup in the .h file, cup's going to have a level, and we're going to fill up the cup until we get close, and it's going to throw a warning, and then it's going to overflow, and it's going to throw an exception, or it's going to throw, but both of them actually are going to be thrown here. So cup is going from NS objects, and we have a level, set level, fill, empty, and print. Kind of basic cup behavior. And then in the implementation over here, we have the initializer. Looks like any other initializer you've seen. The level is going to return the level. The set level. And here's the interesting part. So now we're going to create an NS exception object. Call it E. Very similar to what we did in Java a couple weekends ago, if you were in that Java class. And the variable is going to be a cup overflow exception, exception with name cup overflow exception. The reason the level is above 100. And then user information is going to send nothing. And then at throw E, which is how we're going to do exception handling. Hardly see this. In fact, it's kind of odd, even in the iOS development, hardly see exception handling being done. Because when are you going to be opening, well, when is exception handling done? Opening and closing files, I don't know, trying and catching for network issues, or database connectivity, but all that stuff is kind of built in, actually. So you can throw it inside of the methods, and the methods will come back with return codes and things. But occasionally, though, you might want to throw an exception. Very similar to what was done in Java, actually. But now we're using the @ symbol because this is Objective-C. And it's not on the method itself. It's inside of the code. We create the object, and then we say throw the object. If we throw the object, that means look for it. And then we could essentially deal with it if we get that. If we can check the value of it and deal with it. So here it's going to be cup. This was a cup overflow. Then we have the cup warning. And then we have a cup overflow exception down here on the bottom. So if it's larger than or equal to 50, or if it's less than 0, you know, these are the different conditions we're testing for. We're creating an NS exception object for each one of the cases, and then we're going throw E, throw E, throw E. So then at the bottom here, we just have the method to fill, to empty, and to print to see what the cup level's at. So this is the heart of the set level method that's doing this. So if we go back to main now and take a look at main, would not have a throw without a try and a catch and a finally, wouldn't we? We wouldn't be so similar to Java, would we? So this is where I say it's very similar to Java. What are we doing in here? We're creating a cup, allocating and initializing it. We have this is random number integer I that we're going to use. So this will work here for I is equal to 0, I is less than 4, I plus plus, cup fill, cup print. As it's filling and printing, this will throw an exception here. This will work. This is going to throw an exception. The exception that's going to be thrown is that if I is equal to 0, I is smaller than 7, I plus plus, well, we're going to fill it up a little bit higher. So cup fill. So on the cup fill call, we're going to try. The try we're going to do is same syntax as you see in Java, same syntax you see in C++ as well, in terms of the try, catch, and finally. Same meaning as well. Try this code, cup fill. Then catch. What are we going to catch? Well, we have to catch either one of the two methods, either one of the two exceptions we're looking for. So if we don't catch it, we're not going to get it. So if we just put the try in here, it's not going to come back for us automatically. We actually have to catch it. If we catch it, what we're looking for is a cup warning exception here, or we're going to catch a cup overflow exception here. And we're going to throw those exceptions when the level gets to a certain, if we go back to the code for the cup, when we fill it, it's going to essentially going to trigger one of these methods. Excuse me, it's going to throw one of these exceptions if the level is past a certain point or equal to a certain point, depending upon those case switches we just looked at. The finally is going to happen at the end. So finally, if nothing gets caught, the finally goes at the end and says cup printed out. We can also throw a generic exception here. We're going to try cup set level to -1, and then we're going to catch this NS exception E that we're going to catch, and inside of it we're going to say print it out, E name string, E reason, and then we're going to use this is a C string cast actually, which is depreciated, but let's see what happens when I run this. I might, in order to get, this is actually going to throw the exceptions. Oops, here we go. So now we have cup level. The first one's going to work for us just fine because it's going to print out 10, 20, 30, 40. And then we're going to have, because we didn't catch anything here, we just filled it. And then down here we're going to say the cup level warning here. We have a warning, warning, warning overflow that occurred at 110. I don't know what we set the levels at, but we overflowed it. Then cup underflow exception down here that we threw. And this was the -1. So where's our underflow? Let me take a look here. Underflow is right here. If it's below -1, we threw it here, but we didn't actually implement this one as a separate class implementation. We're just throwing it. We could put stuff in here to do something. Garbage collect, delete objects, send a message out, do something. which would mean our program is really failing and we need to notify somebody or do something or close it down. We can also put it in here in terms of the catch. So these are kind of generic because, well, you don't really do anything with them. We just want to throw them. We're going to throw, these are basically placeholders to say, hey, we reached this level, and if it reaches this level, then we're going to throw this exception. If you throw it, you can do a try and a catch, and if you catch it, then you can deal with it either in the catch clause, or you can deal with it in the exception itself, in the object. The object itself can do something when it gets initialized, actually, when it's thrown. Anyway, so that's kind of an example of the exception handling as it applies towards Objective-C. It's very Java-like. Very Java. Yeah. Very Java-like. Alright, so that was the last of the examples I failed to show you within the first month or so of the class. But we caught up and we got them now. Alright, that was in the B code, so I'm going to throw this so we don't need this anymore here. Alright, so we actually have some time left. So the one that we're supposed to be doing for this class is the one that you're going to need for the iOS class, for the alarm clock. This is now our tutorial time of the day. So we have choices. We can do the animation one, and I think I'm going to do that one actually. And then save the notification one, because that's the one that's going to help the people in the iOS class who are doing the alarm clock. So I'm going to stop this video though so I can start it up logically.